Okay, so today we are going to start delving into some theoretical concepts on databases, right? So last class we talked about triggers and how we can write triggers for certain cases that could handle certain cases for us automatically. Any questions on triggers so far? Because so homework 4 will have some questions on triggers, but mainly it will have questions on creating your own materialized views, right? So if you remember last class, we talked about how we can have views, and we can also have something called a materialized view. That was in essence a view that was stored on disk as a table, right? So that we don't have to recompute it every time, so that if it's a large enough data, we can actually read it from the disk itself and then make our lives a bit easier, right? So today, mainly, we will start and basically for the next two lectures, we will talk a bit about database performance, right? So essentially, we talked about writing queries, we talked about getting data from the database. We will start our discussion now with so how can I make a particular query, or how can I make my database a bit faster in cases where my database implementation is dumb and I would have to like help it around and make things faster for it to compute, so to speak, right? So whenever we talk about database performances and optimizations on that, essentially we are talking about two things. One would be where we are accessing data from the disk, that is your hard drive, that you're accessing your data from a physical storage. So how do we optimize that so that it can retrieve data as fast as possible? And the other part, which we will start from the next lecture, is planning. So how do I, or how does a database plan on a particular query and order the query such that it can get you the result as fast as possible? So we will talk about those two things. So for you guys might have some experience about the planning part already. So if you remember, we had an entire discussion about correlated subqueries, right? And we said that why are correlated subqueries so slow, right? Why are they so slow in order to retrieve certain data from it? Sometimes I remember that I once worked with a code that had a correlated query that for each query it took about 3 seconds. Uh, Again, why, right? I mean, even if it is 3 seconds, that is 3 seconds too long, and I really don't want it to take that much time to actually retrieve a query if it is a query that is executed numerous times over the life cycle, right? So essentially, we talked about why are correlated subqueries so slow, and we also discussed about how not all correlated queries are slow, right? I mean, so we can rewrite a particular correlated query if possible so that it becomes decorrelated, and then essentially that makes our life faster. And why was that? Because in case of correlated queries, the main performance bottleneck that we had was this inner query that needed to be run for every row that is to be computed in the external query, right? So the entire inner query needed to be run again and again for every row that we had to execute in the, we had to generate for the external query. And that became an issue, right? So that is why sometimes correlated subqueries were quite slow. Now, if your database is very smart and it has a good planning algorithm in the back, then it can sort of take your correlated query and then plan ahead so that it can decorrelate the query on its own and then execute the decorrelated version of your query to make it faster. So that is the planner component of your correlated queries, right? So that is one part, and that is one way of making your queries faster. And we know that if our database planners are smart enough, they would do it on their own. But usually there are times where the database is not that smart, right? In order to make your queries faster. In those scenarios, it is usually the case that the internal algorithms that the database uses to plan stuff is not sufficient to decorrelate a particular query. And in that scenario, it would be the database designer that would actually figure out a way to decorrelate the query and make it faster, right? So that is one. So as I was saying, so that is one part of this thing, that is optimizing your queries. The other part would be that given that your databases are stored on disk, how do I make these disk accesses faster? So there are two components to optimizing them. This class, essentially, we are going to talk about that physical storage and how can we make the physical storage, accessing data from physical storage a bit more faster, right? Yeah, so today we will talk about mainly the data storage and access methodologies. So in essence, overall, this entire lecture is geared towards the concept of indexes. And how do we create indexes? What are indexes? Why are they needed? But at the end of the day, it is a really simple concept that just requires a single query or a single statement to create a particular index, just a single line, and that is all. But we need to understand before we understand, before we write that particular query, we need to understand why we need indexes in the first place and what are indexes in the first place, right? Okay. And next time we will talk about planning, and relational algebra will make a comeback again. So we will do these things quite quickly, because these are concepts that would play into, not for this course mainly, but mainly for more advanced database and data science courses, right? So they would build on top of these performance level metrics that we will talk about today. Okay. So disk access, right? So let's talk about disk access first. So we know that all databases at the end of the day is still stored in your hard drive, right? So all databases are still stored in your hard drive, and they are in essence stored in terms of files. So imagine this scenario that uh, uh, if you're accessing data from your main memory or your RAM, that can usually take about tens or hundreds of nanoseconds, right? So that is usually about 100 clocks that are required to get the data from the main memory, and then in essence, load that data into the CPU structure and then essentially deal with that. But again, 100 clocks is still too slow, right? Even from the main memory, 100 clocks are very quite slow. I mean, I can do a lot of things in 100 clocks, right? Now imagine getting the data from the physical storage itself, like loading the data from the physical storage into main memory. Now that requires potentially tens of hundreds of milliseconds now. That is, in essence, not just 100 clocks, it might lead up to a million times more amount of uh, resources in terms of time that is required to load the data into memory and then work with it, right? And now we are talking about disk storage type stuff, you know, like those reading heads and reading blocks of data from those disks, magnetic disks and those sort of things, right? So we would like a mechanism that essentially would make our life easier, in the sense that we would want to be able to access the database, even if it is stored in the file system, but we want to be able to access that database data as fast as possible, or make some changes to our table such that we add some structure to our data that would allow us to uh, query our results as fast as possible. Because we can't like get around this concept that we won't use a disk, right? We will need to use a hard drive at some point to store our data. There are database systems nowadays well, very few database systems nowadays that actually are completely on memory databases, right? So they are not designed to be used with a hard drive. Their entire data resides in the main memory, and that makes it a bit faster. But if you think about it, even then, there are other questions that arise, right? What happens if my system crashes? What if happens if my power goes off? And what happens to the data in terms of that? So these are all legitimate questions that you can ask. Um, so just an aside, so these sort of memory based database systems usually have some mechanism that have the data in some physical storage, but they work with queries, they work with a set of transactions and queries that can actually recreate the data in case of a crash or something like that. So let's forget about that. So in essence, we want to be able to optimize the database such that we need to access the disk as less as possible. That is the entire goal that we would like to strive towards. Okay, so fairly straightforward stuff. So essentially, um, so imagine what happens when you actually write a query, right? So essentially, when you write a query, when you're executing the query, your database actually plans multiple possible equivalent queries that would result in the same data, right? So if you say that, okay, join this as a Cartesian product and then get me the projection result of this thing, maybe then select and then select on based on some of the attributes, your database would then plan that, is a Cartesian product the best thing to do, or should I just do some other join operation, or should I just select the rows first and then perform the Cartesian product and things like that. So there are many possible equivalent plans that would still get you the same result, but some of those plans might be less expensive in terms of time and resource cost than the other plans, right? You guys can visualize that, right? So essentially, your database would then plan ahead and then figure out which plan would actually cost the least, and then it would essentially choose the plan that would cost the least to get you the result as fast as possible. So your database thinks about many different things in this scenario. For example, it thinks about access paths. We will talk about access paths in more detail later, but essentially access paths are the planner's way of figuring out what algebraic operations to perform first and what are the order of the operations that you need to perform that would make my query the least expensive as well as getting the same result as fast as possible. Right? Okay. And also it looks at the algorithms that it has in its disposal to actually get the data from us for us. So essentially, what type of join operations does it have? What type of select operations? What type of sorting mechanisms does it have? And it also looks at the nature of the data itself. So, nature of the data depends upon many different things. So imagine the case where you have, I don't know, sales data for a particular company, right? And you can imagine that it is a US based company. It has stores all the way across all of the states in US. But you can imagine that some states in US would result in more some states in the US would result in more data compared to other states. So, for example, California and New York, where a large population lives, you can imagine that those states would have a lot more data to be processed compared to a state like, I don't know, Idaho or something like that, right? So, essentially, your database plans over those sort of things, and that is what